We're going to talk about the digital functional twin, and of course we're going to do that in the context particularly of autonomous and electric vehicles. Here's the agenda that I'd like to follow for the next 40 minutes or so. We're going to talk about innovation and the need to rethink product development, and then spend some time on digital twins and functional systems engineering. I'll explain 3 principles that I think are important in this subject, and then give you some examples of how those principles we can turn into reality with the tools, before just summarizing and a call to action. So let's get started with innovation. I think we all know the world that the automotive industry is in at the moment. It's a fantastically exciting time. Lots of predictions about what's going to happen, what's not going to happen. And some of them, by the way, are pretty scary if you're a CEO, just for example. Here's an interesting quote from a gentleman called Gene Munster. Gene is the managing partner of an organization called Loop Ventures, and you can read this quote for yourselves. It's from a couple of years ago. In the future, of the 8 major car makers today, only 2 or 3 will be relevant. Okay, and maybe there's some people in this room that are hoping your company are going to make some of those irrelevant. So pretty challenging from a business perspective. That, of course, is talking about the automotive OEMs, but I'm sure some people, again, in this room are from the supply industry, and suppliers must be agile as well. So you can see this particular quotation that I've taken from a McKinsey report just published a couple of months ago. You can see the separation of hardware and software with technologies such as AutoSAR, adaptive AutoSAR, maybe off-board computing and so forth. You can see they're predicting will fundamentally change the nature of the value landscape, reduce barriers to entry. So there's some pretty challenging business problems to go and solve. But probably most of us in this room are engineers of one sort or another. And so we've got to think about what's the future, what's needed in the future. And it's actually pretty difficult to predict the future, I think, from a technical standpoint with the situation we're in at the moment. Here's some data that was published, as you can see, in 2014. Okay? It's a pretty well-respected organization, Deutsche Bank, their global industry conference. And you can see they were forecasting, predicting 5 years ago, whatever it is, that by next year, 2020, that there'd be maybe 30 million lines of software, embedded software in a car, and maybe 10,000 network signals. Well, of course, we all know that that turns out to be completely wrong. You know, there's cars driving around at the moment with 5 times the amount of embedded software versus this. So it's pretty hard to forecast the needs and the technology that the industry is going to need. But what I think we can say is that EE, electrical, electronic, including embedded software, systems development is becoming much more complex. We talk about the mega trends in the industry. They're often referred to as CASE, connected, autonomous, shared, and electrified. And in fact, those 4 boxes across the top, that's what I mean, V2X, so connected car, autonomous operation, of course. Shared, I'm really talking about there the new entrants and the new business models for monetization, and of course, powertrain electrification. And in turn, those trends are driving some other things. For example, of course, we all know that autonomous operation in particular is driving additional requirements for functional safety. Just for example, ISO 26262, that kind of thing. The need for shared cars perhaps is going to drive dynamic configurability, that maybe today the car has got a certain set of capabilities and then it goes off to somebody else and tomorrow it's got a different set of capabilities. How are you going to do all of that and do it safely? It's really becoming a very kind of challenging situation. But the automotive industry is not alone with these challenges. I've got a nice quotation here from a guy called Paul van der Heijden. I know Paul quite well. He works for a Dutch company called ASML. ASML make these fantastically complicated machines that fabricate silicon wafers, okay, chip fabrication equipment. And you can see that quotation there, that complexity is rising at such a rate that they can't solve the problems just by adding more engineers. They need to rethink how they do their product development. And in fact, when you speak with Paul, he'll say, look, more engineers, more errors. Okay, you're getting into a kind of terrible cycle where you just can't get the product finished and designed. And we're seeing this in lots of different industries. Obviously, in the automotive industry that we're in, similarly, off-road vehicles such as agriculture, but the same goes in aerospace, in rail transportation, in complex medical equipment, and things like that. The possibilities and the needs that electronics and software are developing is causing a real challenge to the industry. How are we going to rethink product development? And of course, a lot of people, including us, say that digitalization changes everything. There's a quote here from CIO.com. Again, you can read it for yourself, of course, that first movers who are really investing in digitalization are gaining a nearly insurmountable advantage already over their competitors. So digitalization really is important as we address this complexity, these challenges. Which of course brings us on to the digital twin. So Don has already spoken a little bit about the digital twin, and there's different types of digital twin. I've tried to represent the three fundamental types here on this slide. Over on the left, the one that's the kind of wireframe thing, that's referred to as the digital product twin. It's a kind of model of what the actual product, a vehicle in this particular case, is going to be, the digital model of the product. In the middle, we've got the digital production or manufacturing twin. Again, Don showed that little movie, which was a simulation, a model of a manufacturing process. Okay? And here you can see from this little image here, being able to simulate the manufacturing with the robots and the humans and all that kind of stuff. So how can you optimize your manufacturing process? How can a digital twin of the process help you? And then over on the right, that's the digital utilization twin. That's the vehicle after it's been built and it's driving around in a city, interacting with other vehicles. Maybe it's gone wrong and needs repairing and things like that. We can model the utilization as well. Now in this presentation, I'm going to focus in fact on the one on the left, on the digital product twin, okay, as we design and develop our products. But as we go through this day, this is an ISF event, you'll actually see presentations that refer to all three of these types of digital twin. So let's think a little bit about that digital product twin. So here we've got the digital product twin up at the top and the real product, car in this case, that again is driving around on the roads and so forth. And if I'm 100% honest, I think that quite often when people talk about the digital product twin, really what they're talking about is the mechanical, geometric digital product twin, or put it another way, mechanical design. And of course, mechanical design is now very sophisticated and well advanced and so forth. You can simulate crashes and vibration and noise and all kinds of different things, do lightweighting and so forth. But it's not enough. It's not enough. You need the digital functional twin. There's a very interesting presentation given at a Siemens event called PLM Connections over in Detroit. It's been rebranded to Realize Live in case you're interested for this year. But given by a guy called Bob Trecapelli, who's fairly recently retired from a senior position in Ford. And that was the title, you can see, of Bob's presentation at this event last year, driving PLM beyond geometric, taking a step towards functional system engineering. And really the point of the presentation is that particularly for things like autonomous, just for example, it's not so much a mechanical problem. This is of course going to be all about software and electronics and things like that. We need to be able to model the EE systems in great detail. And that's what the digital functional twin is about. We need to add in some of those different domains that Don was speaking about, such as electronics, electrical networks, embedded software, and so on, and model and leverage those models with just the sophistication and capabilities that can be done with the geometric product twin today. And if we can do that and build that functional, that kind of behavioral, if you like, digital twin for the electronics and software, then that's what's needed to progress this subject. Now you may have noticed in the presentation title of Bob Trecapelli that he was talking about functional systems engineering. So let's just come on to systems engineering. Again, I've got a couple of quotes here. That top one is actually from the US Department of Defense. You can read it again. Systems engineering provides the foundation on which everything else is built. And actually the DoD is now favouring contractors, defence contractors, that can demonstrate to some certain criteria that they are formally adopting systems engineering models, or business models, processes. And then the lower one is from Brett Hillhouse. Some of you will know Brett from IBM. This is a quotation from a few years ago, actually, in the Hansen Report on Automotive Electronics. Nice bold statement: the automotive industry needs more systems engineering. So what about systems engineering? What do we mean by that? Maybe some of you in this room have got degrees in systems engineering. It's a big subject. Let me try to cover it in a kind of simple way, if you like. The human body is often referred to as or used as a good example of what a system is, and hence what systems engineering is. You've got all of these different systems. You've got a circulatory system, a skeletal system, a muscular system, and so forth. But it's only when you integrate those together that you get something useful. You get somebody that can stand up and make presentations, or can compose music, something like that, for example. You get emergent behavior from integrating these systems together. And by the way, it's not always positive emergent behavior. Maybe that human being drinks too much, just for example. And you can start to see, well, there's an analogy here. Maybe that's a functional safety problem if I think about my vehicle in this way, for example. You'll also notice that these are different kind of disciplines. If you go to the doctor, you're probably not going to go to a neurologist if you've broken your leg, because these are different kinds of skills and so forth. So if you think about the human body and use that as an analogy in your mind, let's do a little bit more detail on this. So there is an organization that's all about systems engineering called INCOSE, International Council on Systems Engineering. And they publish, of course, lots of documents and advice and things like that. Of course they do. If you boil down what they kind of mean by systems engineering at INCOSE, I think there's really four things that characterize systems engineering as distinct from component engineering. One is that it's holistic. Two is that it's requirements driven. Three, it's got a strong orientation towards verification and validation. And number four is, these are my words actually, algorithmic transformations between abstractions, model-based systems engineering. And that's actually that generative process that Don was talking about just a few minutes ago. And I'm pretty sure that this is right because the CIO of INCOSE actually works for the same organization that I do, and he did verify that this is okay. So we're in good shape. Now in this presentation we're going to cover all of those, but in particular two of them, numbers 1 and 4, so the holistic side and that model-based systems engineering, or if you like, generative process. So let's just think a little bit about holistic. That's easy to say, but actually quite difficult to do. So let me give you an example. Let's imagine that there's a new law somewhere in the world, and it's all about braking distance. We've got to reduce the braking distance from a certain speed or something because of some new legislation somewhere in the world. So probably most of us in this room are engineers of one sort or another, and we're probably thinking, well, I better start thinking about mechanical modelling of the friction of the tyre on the road and things like that, the hydraulic system, energy recovery if it's an electric or hybrid vehicle, then of course the braking is related to energy management, probably to the software controls in the ABS and all that good stuff. All those engineering things. But it's not holistic. How many of us thought that this is also going to impact the insurance rating? That now if you can stop the car faster, you've probably got a safer car, you can probably have a lower insurance rating, and that's useful again for your marketing department to either say the cost of ownership is less because of insurance. Now you may say, well Nick, that's a bit of an extreme example. I could have replaced it with a different one. I could have said, well, who of us thought about supply chain integration? If we've got some updated software control or something, probably that's going to be delivered by a supplier. So it's quite easy to say, but actually quite difficult to get right unless you've got some process, some infrastructure, some data model and so forth to deal with all of this. So let's talk about systems engineering a little bit more. We've said that very often this really has to be driven from requirements, just for example, and often the beginning of the process is going to be about requirements and then some form of functional modeling, very kind of abstract, if you like, behavioral modeling. And there's various tools, there's various languages available to do that. Some of you may know of SysML, System Markup Language. That's one way of doing it. SysML2 is in development as we speak and so forth. So a lot of people will have some infrastructure and some capabilities to do requirements capture, to do functional, abstract functional modeling, and so forth. And then we've also got, you remember, a lot of verification and validation, different types of verification and validation. And just to take a little kind of sideways step on that particular subject, this is really getting very sophisticated now. You've already seen from Don some of these movies from simulating driving in real road conditions. The couple of boxes there on the right, those are things called emulators. Okay? Emulators are a sophisticated combination of kind of hardware and software for really complicated electronics and software verification and testing and so forth. So the technology is developing really quite fast for verification, validation, and so forth. But again, in my view, this is not enough. It's not holistic, just to say we're going to do some requirements capture and some abstract modeling in SysML or whatever language we choose to use, and then we're going to do some verification and validation. That's a good thing, don't get me wrong. It's vital, it's important. But it's not enough because it doesn't speak to the implementation across these different domains that we've got. And so I would say that you need to add in the different domains. Sure, mechanical, but software and networks and electronics and electrical and so forth. And you can see again, I've gone back to my analogy of the human body because these are like different disciplines. We've got the skeletal guy, maybe he's more interested in the mechanics of the thing. Maybe the software guy is more interested in the neurology of the thing and so forth. And what I've tried to do is to kind of represent this. You can see I've put those a little bit lower than the two sides. And what I'm alluding to there is the systems V. I expect many of you are familiar with the systems V, where you go through different levels of abstraction, drill down to detailed design, then kind of integrate and verify everything together. So in my view, we do need to go beyond just the systems definition on the left and the verification and validation on the right. We need to get to the real implementation. So what are the things that are going to make that happen? What do we need to be successful with this? I think there are three principles that really will make for success with this kind of process toolchain and so forth. And they're written down here, three of them: data coherency, being built to integrate, and advanced automation. And again, Don touched on, in fact, all three of these in his introduction. So when we talk about data coherency, what I mean by that is that we've got to be able to link all of the different data elements together. I've got some little screenshots here. You can see going through a few different kind of abstractions or disciplines, if that's the right word, your requirements, functional design, platform design, and so forth. You can probably see, I hope you can see at the back, that the three screenshots on the right are actually taken from the same tool set, from the Capital tool set actually that Don mentioned. And it's reasonably easy to link the different data elements together with a technology such as indexing, such as Google use. That's why I've given, we're in Silicon Valley, we'll have the Brennan Page paper about data indexing, for example. But the one on the left, that's a different tool actually. And yet we still need to have data coherency across the tool chains. We're starting to come on a little bit to built to integrate actually. So we do need to be able to link the data, objects and so on, maybe a requirement to a function or something like that, just for example, for this to really, really work. So we do need to not only have data coherency within a particular organizational tool set, but across tools, or else we're not being holistic. And that does lead on to number two, which is built to integrate. And maybe some of you have heard the phrase the API economy. I've given some references down there that you can easily find. So if I take that little graphic there, with the different domains and so forth, Siemens absolutely can supply all of the tools that address those different subjects. I'm delighted to, of course. I bet you that there's no organization represented in this room that buys all of their software tools from a single vendor. Maybe you use Siemens for some of it, for NX, but maybe you use, I don't know, MathWorks or IBM or whatever it might be. We've got to be able to integrate these tools together and do it robustly. I was speaking some months ago actually in the aerospace industry and talking to someone who just in the electrical domain, the IT manager was having to maintain over 250 brittle bilateral interfaces to integrate different tools, some in-house, some commercial tools and so on from different vendors together. And it was almost impossible. Every week something broke when some version got upgraded or something like that. We can't live like that. Fortunately, technology does come to the rescue for this kind of thing. Standards absolutely help. You mentioned AutoSAR a little while ago. That would be one. Another is something called OSLC, Open Services for Lifecycle Collaboration, which is quite a mature technology now. It's used in banking and lots of different things. You can absolutely apply this OSLC technology, which makes for a very resilient set of integrations, interfaces. So service discovery, if you like. You can absolutely use that kind of technology. And then the third one is this advanced automation. There's many, many examples, but I'm going to come back to the one that Don gave, this generative design, which, as Don mentioned, is used across different domains. We've got over on the left there, topology optimization. That's in the mechanical world, where you're using or asking the software, the algorithms, you give it some constraints and say, develop for me the best shape. It's the lightest weight or whatever it is within those different constraints. It's absolutely used in the integrated circuit industry. Remember Paul van der Heider's quote, more can't do it just with people. Well, you can't do that with integrated circuits either. You have to be able to generate or synthesize the design from higher level inputs, higher level abstractions. Code generation, low-level code generation would be another example of that. And you absolutely can, as Don said, apply that now across multiple domains where you've got inputs, relatively simple or simpler, high-level inputs, some automation to get deterministic outcomes, correct by construction outcomes. That's what this idea behind the generative flow is. Executable specifications that will take you from the input abstraction, to the output, the next abstraction, next level of detail. And as Don showed, this now can be applied across many different domains, whether it's in the manufacturing area or the design area, for communications and networks and so forth. The documentation. You can generate documentation from higher level abstractions. And this is kind of what it looks like in the software. There's a little screenshot here of a dialog box. Again, hope you can read that in the back there. You don't need to be a Java programmer or anything like that. There's kind of natural language, human language that you can go and put in your IP, your constraints, these rules. So if you want to capture your company IP, this is how we do it. Then, of course, you build and develop rule decks that capture and then automatically apply the intellectual property using the generative process. You can probably see, if you can read this, a few examples. The one near the middle there is all about, we're going to implement a CAN bus, data bus, that respects the specifications of CAN, controller area network. So, Don, you asked a little couple of interactive questions. I don't know if anyone can shout out, how are we going to implement this? As you know, in some geographies, high voltage cables on the vehicle must be orange. That's kind of visually distinctive for service technicians and so on. What are we going to do? Are we going to write a rule that says something? What do you reckon? Something like, if high voltage color equals orange. Pretty simple. Well, you can do that absolutely right now today, and they will always be orange when the final implementation comes. And what that means is that we're getting, I think, reasonably close to what I would call executable requirements. So we come back to this same graphic that I had before. Imagine, and I've just made this up, imagine you had a requirement, maybe it's a legal requirement or something, that says wires carrying safety critical signals, you must terminate those with with gold-plated terminals, okay? So they don't corrode and stuff if there's water or whatever. Now, the requirement is right kind of upstream, and for various good reasons, actually, you probably don't want to select those terminals until quite late in the process. So, can we do that? And I think the answer is yes. You know, you can have safety equals yes in the requirements. The functional design, that will carry through because of the built to integrate and the data coherency. We've now carried that particular attribute through into a functional design. We'll carry it through into the wiring design. We'll carry it through into the harness design. And now you've got an attribute on a wire that implements a signal, that implements a function, that implements a requirement, and you'll automatically select gold terminals just like we automatically selected orange cables for that EV situation. So I think we're getting reasonably close to executable requirements. This is a simple example, but it can be done today. Okay? So just to kind of summarize where I've got to so far, what we're going to do is to integrate lots of these different domains together to optimize the outcomes and to verify the outcomes. That's really the purpose, what we can do with the digital functional twin. And with that, there's lots of good things that we can do. You know, we can optimize, we can verify, we can share, we can reuse, and so forth. The optimization one is an interesting one, I think, because here's an example of some real-time metrics that are generated on the fly as you develop your design. These are looking, if you take a look at the one on the right, for example, how much of my network bandwidth is being consumed with this design versus that design. What if I add an extra function? Locate it on this ECU, but it's got to talk to that ECU. Is that feasible? How can I optimize the positioning, the distribution of the software, and things like that? So you can really make a lot of fast progress, get away from that. I can only do it once because I haven't got time to do it multiple times that Don spoke about. So all of those things are good, of course, but probably the most important thing that this kind of process enables really is innovation. Because with a lot of this automation, with the data coherency built to integrate and so forth, really what you're doing is you're freeing up your engineering talent to do what they're good at, to innovate. Not to, transcribe data from one place to another, not to go and check things manually and highlight with a Sharpie, which, by the way, I still see around the industry from time to time. You're really freeing your engineers to innovate. And of course, in the end, that's going to be part of your competitive advantage. It's going to be a way of attracting and retaining engineering talent. So, is this real? I've said a couple of times, yes, some of this stuff can be done today. I've got a little flow, it's similar to the one that Don put up, and we're talking about systems engineering, and there's various subjects that come up, such as simulation and verification and so forth, being able to integrate with mechanical CAD, with ALM, with PLM, workflow controls, and so forth, and wrap that all around with a built-to-integrate kind of capability. And what I'm representing here are some of the tools, the capabilities that we have in the Siemens portfolio. Here are a few product names. Maybe you're familiar with some of them. I'm not going to talk about them in any detail, but maybe a lot of you are familiar with Teamcenter, just for example, the PLM system. The one in there, in red there, is Capital, and there's several presentations in this event about the Capital tool flow. It's got all of those characteristics. It's got the characteristics of data coherency, of being built to integrate, of advanced automation, such as the generative flow. And you can get some really spectacular results from applying these technologies with Capital. These are real advantages that customers have measured and communicated to us. The one I'll just focus on, verbally, is number one. Okay, so $50 US dollars per vehicle, per car, cost reduction. Now that was from a traditional high volume manufacturer. They'll bite your hand off for 5 cents, never mind $50. So you really can get some pretty important advantages from applying this kind of technology. And you can put that qualitatively as well. There's a couple of snippets out of press releases that I've got here, one from Tesla, as you can see. it was interesting that in fact, although of course Tesla, electric vehicles and so forth, actually the challenges they particularly had that Capital was able to solve were all about configuration management, configuration complexity, and then supply chain integration, communicating change in particular with their suppliers. And then that lower one, that's actually taken from a Japanese company that specializes in systems development, PDS, and they're seeing Capital as a true collaboration platform so as they can get their products to market faster. So, if I try to summarize what I've said over the last few minutes, that we have to go beyond the geometric digital twin and really put in place a functional digital twin, particularly in these EE domains that we all live in. I think that there's three principles, the three that I mentioned before, that are absolutely necessary if you're going to make this a success and make it a reality. You need to use tools, develop processes and so forth that follow those principles. And if you can do that, then there's some real genuine, tangible, hard benefits that you can come and get. And in my view, again, we'll go back to Paul van der Heijden, I think it's impossible to think of the future unless you're using these kinds of technologies. So my call to action, well, it could be, well, go and do it, buy the tools and stuff like that. In fact, I'd be delighted if you go and buy the tools. But actually, it's not that. My call to action is an organizational one. So again, there's a paper here, it was published in ProStep again a few years ago, and the subtitle of this paper, which as you can see is about systems engineering, is much debated, seldom really applied. Now I think that is changing. I think the industries, automotive and then rail and aerospace and so forth, I think that is changing. Remember that DoD kind of instruction, you've got to build things on systems engineering principles. I think that is changing. But my observation is that actually it's changing faster, adoption is quicker in the new startup OEMs, the challengers, if you like. The more traditional, kind of 50, 100-year-old OEMs, they find it much harder because they've got so much legacy, organization, and process. So my call to action is really for the managers in this group is, I don't think that technology is your problem, I think organization is your problem.